You sign up for a 100 megabit internet plan, but when you actually start a download, the computer reports a speed of only 12 megabytes per second. It feels like a mistake, or perhaps a clever marketing trick. In reality, it's a simple difference in measurement. To understand why those numbers don't match, we have to look at the smallest possible unit of digital information, the bit. It takes exactly 8 bits to build a single byte. Providers advertise in megabits because the numbers look larger, but your computer measures in bytes. When that 100 megabit promise is divided by 8, it equals the 12.5 megabytes per second you actually see. At the very bottom of this scale is 1 bit per second. At that speed, sending just the letter A, which is 1 byte, would take 8 full seconds. While no modern connection is that slow, the bit remains the first rung on a mathematical ladder. By multiplying this unit by 1,000 over and over again, we can map the entire history of how humans connect. Multiply that 1 bit per second by 1,000, and we reach kilobits per second, or kbps. This was the ceiling for the first 1G and 2G mobile networks. In the kbps era, mobile data was limited to text and basic emails. Even a simple, low-resolution image could take several seconds to crawl onto a screen like this one. Another jump of 1,000 brings us to megabits, the speed that defined the 3G and 4G era. This increase in bandwidth changed the mobile experience. For the first time, phones had enough capacity to handle video streaming, social media feeds, and app downloads. Multiplying by 1,000 once more brings us to gigabits. If megabits are a bicycle, gigabits are a bullet train. This is the speed of 5G and high-end fiber, where massive HD files move almost instantly. These 3 steps define the consumer experience. Yet, even our fastest gigabit connections carry only a fraction of the data volume moving through the hidden infrastructure that keeps the global internet online. Beyond the home, we enter the tier of terabits per second. This is the internet's backbone, where tech giants move enough data to stream millions of 4K videos simultaneously. To prevent global systems from crashing, these massive data loads travel through industrial-scale hardware, largely flowing through the undersea cables that connect the world's continents. The next magnitude is petabits. In 2025, researchers in Japan pushed fiber optic technology to its limit, breaking the 1.02 petabit barrier in a controlled environment. At that speed, you could back up the entirety of YouTube's daily global uploads in a single second. At this infrastructure level, the challenge isn't just raw speed. It is a race to maintain perfect synchronization and data integrity across thousands of miles of physical distance. Scaling to exabits per second, the physical properties of glass and copper become a bottleneck. Traditional fiber optic cables simply cannot carry this volume of information. Reaching this level requires a shift towards satellite laser links and quantum data transfer. These systems are the prerequisites for the massive data pipes needed to support planetary-scale networks and long-range communication with deep space missions. One step higher is the zettabyte. A 1-second zettabyte connection could theoretically copy every piece of data humanity has ever created. The final magnitude on our ladder is the yottabyte. This represents 1 septillion bits moving in a single second, a number so large it makes every previous speed on this list look like a standstill. At 1 yottabyte per second, you could theoretically transfer the entire contents of the internet in a fraction of a second. This climb from a single bit to the yottabyte is more than a technicality. It is a roadmap of human progress. We began with the 8-second struggle to send a single letter, and we are moving toward a future where the sum of all human knowledge can be shared across the stars.